Before we look at our next type of variation, let's look back at our problem in the thunder there. And maybe just a slightly more eloquent, succinct way, I should say, way to describe what K is. So yes, K does refer to, in this problem, it takes 1 second for the sound of thunder to reach your ear for every 10,080 feet away you are from where the storm is. But what that means is that K is the speed of sound. Right? Inverse variation. Another function that's frequently used in mathematical modeling is f of x equals k divided by x, where k is a constant. If the quantities x and y are related by the equation y equals k divided by x for some constant k not equal to 0, we say that y is inversely proportional to x, or y varies inversely as x. The constant k is called the constant of proportionality. All right, so if you're told that two quantities vary inversely, this is the formula that you would use. The graph of y equals k divided by x for x greater than 0 is shown in figure 3 for the case where k is also greater than 0. It gives a picture of what's happening when y is inversely proportional to x, and that's our diagram, figure 3 there. Inverse variation. Boyle's law states that when a sample of gas is compressed at a constant temperature, the pressure of the gas is inversely proportional to the volume of the gas. Right? So let's think about what that's telling us. It's telling us that the pressure of the gas is inversely proportional to the volume of the gas. So in other words, so the volume is going to go in the denominator because they are inversely proportional. That's where that piece of information there tells us how to set up the equation. And this is an example of inverse variation. Suppose the pressure of the sample of air that occupies 0.106 meters cubed at 25 degrees Celsius is 50 kPa. So that's just the units. That's just a unit for the pressure. So notice this is a measure of volume. Cubic measure is volume. This here is temperature. And this is our pressure. Now temperature here won't play a part in this particular equation here. That just happens to be some information. So find the constant of proportionality and write the equation that expresses the inverse proportionality. Sketch a graph of this equation. So P, let's just use P for pressure, equals K divided by V. P is 50. K is what we're solving for. That's our constant of proportionality. And the volume here is 0.106. Right, if we want to solve for K, we just multiply both sides by 0.106. So we have 50 times 0.106 times 50 is equal to K, and that means K is equal to 5.3. Right, so that's A. That's our constant of proportionality. Write the equation that expresses the inverse proportionality. All right, so now once we find K, we can write the equation. Our equation is P equals 5.3 divided by volume. Right? And so now we can use that to find either the volume or the pressure. All right, and we're asked to sketch a graph. All right, so well, volume has to be positive. So we're going to stay on the positive side here. And obviously we can't have 0, right? Because if you divide by 0, that would be a problem. All All right, so let's think about the scale. Let's graph the point we're given, right? We're given the point 0.10650. So let's have 1, 2, 3. Let's have this go up by 1/10. That'll work. I even oriented the board. Or not 1/100th, 1/10th, excuse me. And let's have the Y scale go up by 10. So that would be, each box is 10, that would be 20. All right, and so we've got 1 point there. We know 0.106, that's just about 0.1, and 50, so 20, 40, 50. All right, this one is not as easy to graph as the linear function is. So let's plug in another value, all right, and then we'll be able to graph our equation here. All right, so let's say we plug in let's answer B and we'll have another value. Let's kill two birds with one stone. Let's answer B and then we'll finish our graph. All right, so B says if the sample expands to a volume of 0.3 meters cubed, find a new pressure. All right, so P is equal to 5.3, and the volume now is 0.3. Just plug that into the calculator. So P is about 17.7. And the units is kPAs. All right, so now we have a second point. Since we need a second point, we may as well just solve the other half of the equation of this problem here. 17.7. All right, so that's 0.3, and it's just a little less than this. All right, this is going to, so our volume is never going to be negative, so that's a vertical asymptote for this graph. This, by the way, although it looks a little like an exponential, is not, because we don't have a variable in the exponent. There, it looks a little better. That's as good as it's looking. All right, so there's our basic sketch for our graph. All right, and now we've looked at inverse variation. All right. In the next example, we're going to combine those together, right? But it's essentially we've got a model, right? We use that model to solve for k, and then we can solve for other values, right? And then our sketch here is just kind of basic idea what the graph looks like. All right, so thanks for watching. I have some problems for you to solve, and bye for now.